Hi guys, in this video, I'm going to be going through section 7.7. So this is going to be a section of notes that we're actually going to do in class, but making this video for you guys so that you can either rewatch or for those of you that are at home, you can stay caught up with what we're doing in class. So we're doing 7.7 today, calculating equilibrium concentrations. And then 7.8, we're going to do representations of equilibriums situations. Those are going to be like particulate diagrams. So drawing diagrams that represent what's going on at equilibrium. So let's get started. So everything in this section of notes is just going to be a bunch of example problems that we are going to go through to figure out what the concentrations of our different substances are going to be at equilibrium. And so the thing about equilibrium problems is that they're all just a little bit different. So I'm going to go through 4 examples of just different types of situations that you're going to come across so that you know what to do when you see them. So in this example, we've got NH3. It's turning into nitrogen and hydrogen over on my product side. It's a reversible reaction, so we see that double arrow there. It tells us how many moles of NH3 we start with and what the volume of that container is. So it also tells me that at equilibrium, how many moles of NH3 are left over. The question, though, is asking us to solve for the value of K. So right away, when I look at that, I should notice, okay, I'm going to have to calculate K. So let me write out what that K equation is going to be equal to so that I know what I'm going to use to solve the problem at the end. So remember our K expressions, we're going to take our concentrations of products. So N2 and H2, that's going to be cubed. I get that from my coefficient over the concentration of my reactants. And then that concentration is going to be squared. So products over reactants, that's my K equation. What I need to do in order to calculate K is I need to find what all of these concentrations are. The concentration of N2, the concentration of H2, the concentration of NH3. And all of those concentrations that I have to plug in have to be at equilibrium in order for me to calculate the K value. So that's what I have to do. I have to solve for those concentrations at equilibrium. Then I can just plug them into this equation when I'm done. So what we're going to do is we're going to use this strategy for all of our equilibrium problems. So I'm going to rewrite the equation down here just because I'm going to label some stuff. So we're going to use what is called an ICE table. Now, ICE, those letters ICE, they all stand for different things. So I represents initial, and it represents our initial concentration. So what I need to do is I need to figure out what my initial concentration is of NH3. Well, if I had 4 moles, remember molarity is moles over liters. I had 4 moles of NH3 to begin with in 2 liters. That concentration is 2 molar. So what I'm going to do is I'm going to go ahead and plug that number in right here. Now, if I just put NH3 in a container, the forward reaction really hasn't started yet. So I actually start with 0 of everything on my product side. You are going to start with 0 with everything on your product side unless they tell you otherwise. So we'll put zeros in there. Now, C represents change. And change is going to be like how much is going to be used up or how much is going to be produced in the reaction. Now, I know that everything on the left side, my reactants are going to be used up. So this is going to be a negative number. Everything on my product side, those things are going to be produced. And so those are going to be positive numbers. And I don't really know how much that is just yet. So what I'm going to do is I'm going to go ahead and plug them in as X variables. So nitrogen is going to increase by X amount. And if nitrogen increases by X amount, that means hydrogen is going to increase by 3X because it is produced 3 times faster, right? And then because of my coefficient of 2 in NH3, that's going to decrease at a rate of negative 2x. So that's my change column. Now, my E stands for equilibrium. That's going to be my concentration at equilibrium. All I'm going to do is I'm going to take these sections and I'm going to combine them together. So 2 minus 2x is going to go here. 0 plus x is x. 0 plus 3x is 3x. So that's setting up my ICE table. Now, my next part in my any equilibrium problem is, well, let's go back. Okay, first step should always be to write your K expression. Second step should always be to set up your ICE table. Your third step should always be to figure out how to solve for x. This is where every equilibrium problem is different. So you want to look at what's given to you in the problem and figure out what you can use to help you solve for x. So in this problem, it tells me that at equilibrium, there are 2 moles of NH3 left over. 2 moles in 2 liters, that's a molarity of 1 at equilibrium. So down here in my ICE table, I'm going to put 2 minus 2x equals 1. So then I can use that information, 2 minus 2x equals 1. Since I know what that equals, I can go ahead and solve for x. X is going to be 0.5. Okay, so that's just some algebra for you to do right there. So then when I'm going to go ahead and solve for my concentrations, I can, this is going to be 1 right here, my concentration at equilibrium for NH3. This is going to be 0.5 because it's just x, right? So I can just substitute this into my equilibrium row over here. 3x, 3 times 0.5 is going to be 1.5. So these are my concentration numbers, 1.5 and 1.5. These are my concentration numbers that I'm going to plug back into my K expression. So now I'm going to go, let me get a different color. Now I'm going to go ahead and I'm going to plug in for N2, I'm going to plug in 0.5. For H2, I'm going to plug in 1.5. And then that needs to be cubed. Let's not forget those exponents. And then for my NH3 concentration, I'm plugging in my concentrations at equilibrium. So that is 1. And then that number is squared. So I'm going to go ahead and calculate K. That's 1.69. No units. That's my K value. Okay, so when we're solving for equilibrium problems, step number 1, write out your K expression. Step number 2, set up your ICE table. Step number 3, figure out how to use the information that you have to solve for x. So that's our first example. Let's go ahead and do another one. Okay, so here's our second example. You can see that I've already set up the ICE table and the K expression. So you may want to pause the video so that you can make sure that you set that up in your notes. So we've got the initial concentration of HF is 2. We've got a K value this time, so we're given different information. I took my initial concentration and I plugged it in here for HF. So there's that. I set up my ICE table with 2 minus 2x plus x for H2 and plus x for F2. Now, the thing that's different in this problem is that I'm given my K value. So when I write my K expression, I know that all of that when I plug it in is going to be equal to 1.5 times 10 to the negative 5th. So remember, step number 1 is to write your K expression. Step number 2 is to set up your ICE table. Step number 3 is going to be to solve for x. So we're going to do this a little bit differently. What I'm going to do is I'm going to go ahead and I'm going to take everything from my equilibrium row and I'm going to plug it into my expression for K, because I know what it equals. So 1.5 times 10 to the negative 5th equals, now for H2, that's an X. For F2, that's an X. I'm going to go ahead, and plug in those variables. Sorry, that should be an X right there. And for HF, I have 2 minus 2X. That number is going to be squared. Now, if I kind of simplify that a little bit. I've got x squared on the top. I've got 2 minus 2x squared on the bottom. Now, here's the deal. When you square 2 minus 2x on the bottom, you'll end up with a quadratic equation. However, on the AP test, you should never have to do any quadratic formulas, so you should always be looking for ways to simplify your equations so that you don't have to use the quadratic equation. You'll get the right answer if you do, but you'll just be working harder than you need to. So if I look at this and I see there's an x squared on the top and then there's a squared term on the bottom, I can square root both sides of my equation. So when I square root both sides, I do have to still square root my 1.5 times 10 to the negative fifth. So I square root that and you get 0.00387. And then that is equal to x over 2 minus 2x. Now, that's still a little bit complicated, but it's better than having to do a quadratic equation. You are going to have to go ahead and bring this 2 minus 2x over to the other side. So you've got 0.00387, and then 2 minus 2x equals x. You're going to have to distribute through. You're going to go ahead and solve for x here. I'm not going to do all of the math and the algebra with you guys right now. I'm just going to show you guys what you're going to do with that. Once you solve for x, then you're going to go ahead and take that number and you're going to plug it in right here, right here, right here, and you will get all of your concentrations at equilibrium, which is what the question is asking you for. So once you get that x value, just go ahead and plug it in and solve for those concentration values. Let's go ahead and take a look at another example. Again, I'm not going to spend a lot of time going through setting up the ice table. This one doesn't even actually have the problem here, but let's say you're doing an equilibrium problem. This is my equation with 2 NOCl and 2 NO and Cl2 over on my product side. Let's also say in the problem that we're given our initial concentration of NOCl as 0.5 and my initial concentrations of my products. Let's also say that we're given K. And the question is to find our concentrations at equilibrium, solve for X. So if I write the K expression for this, I would have NO squared on the top. I'd have Cl2 and then NOCl squared on the bottom. So when I take my expressions from my equilibrium row, oh, I didn't set that up. This would be 0.5 minus 2x. When I take those and I plug them into my K expression, I'm going to end up with 2x squared and then x. On the bottom, I'm going to end up with 0.5 minus 2x squared. And all of that is equal to my K value, 1.6 times 10 to the negative 5. And my goal here is still to solve for X so that I can plug it back into my ice table and solve for the concentrations at equilibrium. So what I have here on the left, all of this is really tricky. We're going to get X cubes and quadratics on the bottom and all kinds of stuff that is difficult to do. So what we're going to do, if you have a really small K value means times 10 to the negative fifth or smaller. Basically what that means is that if you have a small K value, that means when you solve for X, it's also going to be tiny. So since X is a super small number, what you can do is you can cross out any X value that is added or subtracted. So I'm going to look at my K expression over here and I'm going to be like, okay, are there any X's that are added or subtracted? This one is right here, 0.5 minus 2x. I can cross that out from my equation. The reason why, since X is so tiny, if I do 0.5 minus a super tiny number, it's basically going to be 0.5 when I'm using the correct number of significant figures anyways. So I can just cross that out. I can't cross out x's that are multiplied though, because multiplying by a small number is actually going to make a big difference. So what I'm going to end up with on the top is I'm going to end up with 1.6 times 10 to the negative fifth. On the top, remember that I need to square that 2. So I'm going to have 4x squared, but then times x. So that's 4x cubed on the top. And on the bottom, I'm just going to have 0.5 because I crossed that out. Just kidding. Need to square it. 0.5 squared on the bottom. From there, that is a lot easier to deal with than quadratics and all kinds of things like that. So you're looking for those x values that are added or subtracted that you can cross out of your equation to simplify the math. From there, we can go ahead and solve for x, which we can plug back into our ICE table and use to solve for the concentrations at equilibrium. That's if your K value is really small, times 10 to the negative fifth or smaller. Okay, last practice problem for today. We've got PCl5, it is turning into PCl3 and chlorine gas. Now we can do ICE tables because remember we can do Ks with concentration, also with pressure. So when I write the K expression and we're dealing with pressures instead of concentrations, we are going to use brackets, not brackets. Brackets are for concentration. We're not going to use brackets anymore. So this is going to be the pressure of PCl3, and we can put them in parentheses, times the pressure of Cl2 for my K expression, and then times the pressure of PCl5. So we can use that. Notice they give us our initial partial pressure of PCl5 is 189.2 torr. So I can plug that in. If this is my ICE table, I didn't leave room on the left side for my letters there. I'm going to start with 0 here, plus x. This is going to be minus x, so I end up with 189.2 minus x. Now, step number 1 was to write the K expression. Step number 2 was to set up my ICE table. Step number 3 is to solve for x. So let's take a look at how I can do that. I used this number already, okay, so I'm not going to be using that again. It tells me the total pressure at equilibrium is 358.7 torr. That means that if I take all of these numbers and I add them together, then it is going to equal 358.7. So I'm going to go ahead and do that up here. So 189.2 minus x plus x. Oh, whoops, I need one more plus x. Plus x equals 358.7. Now, negative x, positive x, those cancel, so I end up with 189.2 minus x equals 358.7. And I can go ahead and plug in for x. X is 169.5 torr. I'm going to take this. I'm going to plug them in all over here. So that means that my pressure, let me get a different color. My pressure of PCl5 is 189.2 minus 169.5 because I'm just plugging it in right here. That gives me 19.7. My pressure of PCl3 is just the same as x, so it's 169.5. My pressure of Cl2 is also 169.5. Now, I could go ahead and I can plug all of these numbers back in here to my expression for K, and I can solve for Kp. So I would end up with 169.5 times 169.5 over 19.7, and you get a big number, 1458. So that would be my K value. All right, that is a lot of different examples of equilibrium problems, but just remember always to start with writing your expression for K, setting up your ICE table, and then using whatever information is given to you in the problem to help you solve for X so you can figure out concentrations at equilibrium and go from there depending on what the problem is asking you. So you guys are working on worksheet 7B after this section of notes. So lots of equilibrium practice, and I will see you guys in class. Have a great day.